Welcome back to part 2 of the chapter concerned with the study of dynamics of a particle. We have discussed so far the basic principles, Newtonian laws, the 3 laws of motion, and we are ready now to use these equations in order to analyze the motion of a given object. So in this lecture, I will keep talking about the force and its relation to the motion of an object. Specifically, I will pick up an application where we apply Newton's laws to determine the motion, the state of motion of an object or a system of objects, a variety of objects. And forces acting on an object can be of different types. One basically important and special kind of forces that could be acting on an object is friction. And we will talk about frictional forces acting on an object during its motion later on. But for the time being, before we have our example, in order to demonstrate how to apply Newton's laws of mechanics to study the motion of a system of particles or objects, we would like to discuss the basic types of forces that are responsible for the motion of an object. Forces can be of different kinds, but for the time being, I will talk about a small number of these forces which are relevant to our discussion. What are the types of forces that we encounter in the study of motion of objects? As we remember, Newton's second law states that the summation of all external forces acting on an object is simply equal to its mass times its acceleration. What are these forces? One type of forces that can affect and influence the motion of an object is its weight. The weight of an object on Earth, for example, is a force. It is the force by which Earth attracts the object. It is the gravitational attraction of the object by Earth. And this force, which is the weight, is always directed downwards. And that's why an object which is let go under the influence of gravity would always travel downward, because it is influenced by a force. What is that force? It is its weight. It pulls it down and it accelerates it. And since a freely falling object accelerates with a constant acceleration downward, which is equal to g and directed downward, the acceleration of gravity, that means the force, according to Newton's second law, the force acting on that object must be equals to m, the mass of the object, times its acceleration downward, which is g, mg. That means the weight as a force acting on the object is equal to mg in magnitude and is directed downward. That's one type of forces acting on the object as it moves. Also, there is another type of forces that can be influencing the motion of an object. For example, if an object is situated on top of a table, the table would restrict the motion of the object and will never allow it to go down. That means the table must be applying a force on that object which is moving on it. Otherwise, the object will fall down. And that force that the table is influencing the object is called the normal force. So, as the object is pressed against the table, it is affecting the table by force, a given force, pressure. The table would feel pressure due to the existence of the object on top of it. And if the object is so massive and great, it will cause the table to break. That means that the weight of the object is influencing the table on which it is situated. So what do we have then? According to Newton's third law of mechanics, if the object is influencing the table by a force, then the table would respond and would have a reaction force that affects the object with an equal and opposite force. So the normal force, another type of force acting on an object situated on a surface, is a normal force acting perpendicular, acting on the object in a direction perpendicular to the surface on which it is situated. So on a flat table, for example, an object would be influenced by a normal force acting on it from the table, which is directed directly upward. However, on an inclined plane, if the object is situated on an inclined plane, then the normal force would be acting on the object in a direction perpendicular to the inclined plane. That normal force is also necessary for us to encounter because we come across such forces as we are studying the motion of an object on surfaces, as we will see in a short while. A third type of forces that we encounter is the tension. The tension, if we have an object that is attached to one end of a rope or a cord, and we pull on the other end of the cord, then there will be a tension applied to the cord, and that tension will pull the object in a direction which is along the cord and in the direction of the tension. That is another type of forces that we encounter when we pull on an object using a cord or a thread or a rope. The other special type of forces that we will not be discussing now, we will leave some space for it, is the frictional force, and that we will leave it until later. So now we will be considering the motion of objects which do not suffer from frictional forces, and we will leave the frictional forces until later in this lecture. So now we go to study the motion of a given system and apply Newton's laws and see how we can apply Newton's laws in order to describe the motion of this object, of each one of these two objects. In this figure, we have two objects. One of them we call the sliding block, which is a block having a mass capital M resting on a horizontal surface, and we have a second block of mass small m, which is hanging. These two blocks are attached to two ends of a cord, and the cord is going around a pulley. The pulley is assumed to be massless and frictionless. For simplicity, in order to limit our study of the motion to the motion of the two bodies only, small m and capital M. The cord is assumed also to be massless, and that leaves us only with two objects having masses, and we can study the motion of these two objects. The first is the sliding block, the second is the hanging block. A quick look at this diagram would tell us the following. It's necessary to identify the forces acting on each block in order to analyze its motion. So we have the sliding block, for example. What are the forces acting on the sliding block? We have one force is its weight, m, capital M times g, which is directed downward. That is one force acting on the object, which it's mass times gravitational acceleration, which is the weight. A second force acting on the sliding block is the normal force. The sliding block is resting on the flat table, and it is affecting the flat table with some sort of a pressure due to its weight, and thus the table is influencing the object or acting on the object by a normal force N upward. The normal force is N. There is also a third force acting on the sliding block, which is the tension in the cord. Notice as the hanging block falls down, it pulls on the cord, and the cord pulls on the sliding block. So the pull in the cord on the sliding block is what we call the tension, and this is a force that pulls on the sliding block. So those are the three forces acting on the sliding block. Two of them are in the y direction, one of them in the positive y direction and the other one in the negative y direction. And the third force, which is the tension, is pointing rightward. The second object is the hanging object. The hanging object is influenced by only two forces. The hanging object is moving up and down, and the two forces acting on it are the tension acting on it from the cord, and it acts upward. And this can be understood by imagining that if we cut the cord, it will be easier for the hanging block to fall. That means the existence of the cord with the tension in it is hindering the motion of the block. So the tension upward is a force acting on the hanging block, and as usual, its weight, small m times g, the gravitational acceleration, is the second force that is acting on the hanging block downward. So when we want to analyze the motion, we focus on one body. So first of all, we consider the sliding block, and we consider the three forces acting on it. Then we consider the hanging block, and we consider the two forces acting on it, and we plug these forces in each case in Newton's second law in order to analyze the motion of each block. We notice that also it is important to remember that as the two objects are attached by a cord, and the cord is inextensible, which means it does not stretch. If that is true, that means the speed of each object is the same as the speed of the other. The two objects would have the same speed, and also the two objects would have the same acceleration as far as magnitude is concerned. The only difference between the two is the direction of their velocities and accelerations. So as the sliding block is moving with a certain velocity towards the right, the hanging block is moving with the same velocity, but it is going down, having the same magnitude of the velocity but downward. And similarly, the acceleration, the hanging block is accelerating downward, while the sliding block is accelerating towards the right. The magnitudes of the accelerations are the same. So we have to draw the free body diagram for these two objects. As we mentioned, it simplifies our analysis dramatically. So for the first object, which is the sliding block, we have here at the center, we have a spot which represents the sliding block, and the three forces acting on it are the normal force upward, the weight, capital M times G, downward, and the tension in the positive x direction. We define the axes such as the x-axis is pointing toward the right, parallel to the surface of the table, and the y direction is pointing upward, perpendicular to the surface of the table. So those are the three forces acting on the sliding object. The free body diagram for the hanging object is drawn similarly, where the spot in the center at the origin of the axis is the hanging block, and there are two forces, as we mentioned, small m times g, acting on the hanging object or block downward, and the tension of the cord acting on it upward. Those are the only two forces acting on the hanging block. So now we move on to the analysis of the motion, and we consider the motion of each block separately. First of all, let's consider the motion of the sliding block. In the beginning, we must remember that the sliding block slides across the table. It does not go up and down, which means that there is no net acceleration up or down. The y component of the acceleration is 0, and from Newton's second law, that entails that the summation of forces acting on the sliding block in the y direction is 0. The summation of forces in the y direction is 0, and the forces, as we noticed from the free body diagram acting on the sliding block, is the normal force up, which would be n vector minus mg vector, because the weight is acting downward, is equal to 0, and that would give us the result n equals mg, which means that the normal force by which the surface acts on the sliding object is simply equals to its weight. That makes sense. The sliding object influences the surface of the table by pushing on it by its weight, and the surface of the table reacts by an equal and opposite force, which is equal to the weight in magnitude and opposite in direction. That is a consequence of Newton's third law. In the x direction, however, there is only one force acting, which is the tension. Thus, the tension in the cord, which is the total force acting on the sliding block in the x direction, is simply equals to its mass, which is capital M, times its acceleration towards the right. So that's the equation that represents the x motion, or the motion along the x direction. Now, we have arrived at two equations. Now we go on to derive the equations which represent the motion of the hanging block. The hanging block is influenced only by two forces, one of them acting upward, which is the tension, and one of them is acting downward, which is the weight of the hanging block. And we must remember that the hanging block is moving downward. That means its velocity and its acceleration is also negative. So the equation that represents the motion of the hanging block is simply T, positive, because it's applied upward, minus mg, because the weight is downward, is equal to minus ma, because the acceleration is downward. And we have written, as you noticed, the acceleration, we have written it as a for both objects, because as we mentioned, the acceleration of the two objects must be the same, but their directions are different. We have encountered the direction of the acceleration of the hanging block by introducing this minus sign to indicate that it is moving with the same acceleration as the sliding block, but it is moving downward. So this is a statement which illustrates what I just mentioned about the fact that the two accelerations are equal because the two objects are tied to the ends of the same cord and are moving together. And now we have these sets of equations that we can solve. And first of all, we should make sure that we have enough number of independent equations, as many as the number of unknowns, in order to be able to solve for the unknowns. So, for example, in this example that we just mentioned, we have the following unknowns: the normal force and the tension, and we have the acceleration. All of them are unknown. So we must have as many equations in order to be able to solve these three unknowns. We must have three equations. If we have four unknowns, we must have four equations. Now we have enough equations to solve for these unknowns. And first of all, we look at these equations and we eliminate t. That means we find how much is t. Let's go back to these equations in order to see what do we have. For example, from here we find that t is equal to mg minus ma, and we replace this value of t, which is mg minus ma, small m, we replace it in the equation which gives t is equal to capital M times a. So we obtain an equation that contains not the tension and the acceleration together, because both of them are unknowns, but rather we obtain an equation that contains only the acceleration and constants which are known. The gravitational acceleration g, which is known, the mass of the hanging block, the mass of the sliding block. So this is the solution for A. That is the acceleration of the sliding block as well as the acceleration of the hanging block. Second, we substitute this value of the acceleration, which we just calculated, we substitute it back into the formula that gives t equals capital M times A. Instead of A, we put its value, which is small m over capital M plus small m times g, and we obtain this solution for the tension. Thus, we have obtained the three unknowns by solving these three equations. We have obtained the value of the normal force acting on the sliding object, which turns out to be capital M times g, the weight of the sliding block, and we have evaluated the acceleration of the two objects. The magnitudes and the directions are known from the way they move, and we have evaluated the tension in the cord connecting the two bodies. This is a demonstration of how to apply Newton's mechanics or Newton's laws of motion to the study of the motion of an object. So once we know the acceleration of the object, one of the objects, the hanging block, for example, we can determine its velocity or its position at any time. We can determine the distance it travels, we can determine the displacement or any other parameter that we might require or be interested in. Now, this past example does not take into consideration the frictional forces. In nature, we have frictional forces that often hinder the motion of an object. For example, if we have an object on top of a table and we push that object across the table, we notice that in the beginning it moves and then it comes to a stop. Why would it come to a stop? Newton's first law tells us that if in the horizontal direction there is no force acting on the object, then it should keep going on with the same velocity and same direction forever. The fact that this moving object, after we push it, after we give it this little push and let it go, after we have let it go, this object comes to a stop. That means during its motion, it is influenced by another force, and that force is acting on it in an opposite direction to its motion. And that force affects the motion in such a way that it reduces its velocity, it accelerates it in an opposite direction to its motion until it comes to a stop. That force is the frictional force. We call this the kinetic friction because it is affecting the object while it's moving. Another example is if we have a massive object, such as a cupboard, for example, or a massive rock, or a car on the street, and we try to push on that massive object, the object does not move. Although we are acting on the object by a force, it still does not move. That means, if we think in terms of Newton's second law of motion, there is a force that is equal to our push and opposite in direction that is acting on the object, such that, in such a way that the summation of all the external forces acting on that object is equal to zero. What is that force that acts on the object which is equal to our push and opposite in direction? that is a frictional force. That frictional force, we call it static frictional force because it is friction that is acting on the object while it is not moving. So we call it static friction. These are two different types of frictional forces, and we might ask, what is the source of this frictional force? On the micro scale, the surface is not completely flat. It has a wiggly surface in a way, pointy points, and has hills and valleys and so on. Each surface is of that type. No surface is flat on the atomic scale. So when the object is situated on top of a surface, the points near the tips of these structures on both surfaces get stuck together. They're cold weld. They get stuck together. And in order to release or to break this force, this adhesion force between the two surfaces at the points of contact, we need a force to be applied. And that is basically the frictional force. Or we can think about it in a different way, that these cohesive forces between the two surfaces would act against the motion of the object as we push it across the surface. One might think that frictional forces are bad or not desirable. In fact, no. Frictional forces are very necessary in our lives, our everyday life. For example, if there is no friction, we cannot walk across the street. Cars don't move. We cannot carry a pencil or a spoon to feed ourselves. If we can imagine what frictional forces are important for, or where the frictional forces come to play in our everyday life, we will realize that our life is impossible actually without friction. So frictional forces, although they hinder motion and they require that we waste some energy in order to overcome these frictional forces, they are also necessary in everyday life. As we mentioned, the static friction is one type of the frictional forces, and this comes to influence the object if we apply a parallel push to the object across a surface. If we apply a push on the object which is situated on top of a surface, if the object does not move as we push it, then the force acting on it would be the static frictional force, as we mentioned a little while ago. The static frictional force is variable because, as we mentioned, keep pushing on a massive object, it doesn't move. As you push more and more, apply more and more force, at a certain point it starts moving, it starts sliding. Thus, the frictional force, the static frictional force, has a minimum value which is 0, which is when the object is situated on top of the surface and nobody is pushing it, nobody is pulling it, nothing is applied to it. So the frictional force, the static frictional force, is 0. And the static frictional force applied or acting on the object keeps growing and getting bigger and bigger as we push the object more and more until it moves. So we reach a value which is called Fs super maximum. That is the maximum frictional force, after which the object starts sliding. So graphically, we can say that the frictional force, the static frictional force, starts from 0 and grows with F parallel. F parallel is the parallel force acting on the object parallel to the surface. If we keep increasing the parallel force and the object does not move, the static force keeps growing until it reaches the maximum. At this point, after the applied force, the applied parallel force reaches the value of the maximum static force, then the object slides, as we said, and there we experience a dramatic drop, a sudden drop in the frictional force as the object starts moving or sliding across the surface, and the frictional force that is acting on it at this point in time is the kinetic friction, which is lower in value than the maximum static frictional force. The kinetic frictional force thus acts on the object if we push it across a surface with a parallel force parallel to the surface, that is greater in magnitude than the maximum static frictional force. This is very necessary for the motion of the object. And thus, the object would move, slide across the surface, and the frictional force F sub k, which is the kinetic friction, is acting on it. In general, as we saw from the figure, from the previous figure, the kinetic frictional force is smaller in magnitude than the maximum static frictional force. This is a general rule. How can we evaluate the static frictional force? The static frictional force is equal in magnitude and opposite in direction to the applied force, to the parallel applied force to the object as far as the object is not moving, which means V equals 0 of the object. As far as the object is not moving, the static frictional force is equal to the applied force parallel to the surface. That means this keeps growing until it reaches the maximum value, Fs maximum, and that value, the maximum value of the static friction, is given by the formula mu sub s times n. That means the static frictional force, the maximum value of the static frictional force, is proportional to the normal force that the surface acts on the object. And the coefficient of proportionality is mu sub s, which is called the coefficient of static friction. Similarly, the kinetic frictional force, which is the force that acts on the object as it slides across the surface, is also found experimentally to be proportional to the normal force acting on the object. And the constant of proportionality is called mu sub k, which is the coefficient of kinetic friction. Now, let's consider one final example where we have an object acted upon by a variety of forces, one of which is the frictional force. Suppose that we have an object that we pull on it and it moves with a constant velocity. if it moves with a constant velocity, that means its acceleration is 0 in any direction. Now, if we look at the free body diagram of the body being pulled with the force T, which makes an angle phi with the x direction, and the other forces acting on this object are the normal force upward, the weight downward, and the kinetic friction in the direction of the minus x axis, negative x axis. Remember that the frictional forces act always in an opposite direction to the motion. So we analyze these forces in a similar way that we did before. We only have to analyze the tension to its two components. One of them is the x component, which is T times cosine phi, and the other one is the normal component, which is T sine phi. Thus, we have all forces are lying either in the x direction or in the y direction. And we apply Newton's second law to the motion in the y direction. We consider only the y components of the forces, which are T sine phi upward plus the normal force upward minus mg because the weight is downward, and that is equal to 0 because the acceleration in that direction is 0. As we mentioned, it is a block that is moving with a constant velocity. That means the acceleration is 0. Similarly, from the x components of the forces, we have T cosine phi, because this is acting in the positive x direction, minus Fk, which is the frictional force acting on the negative x direction. The summation of these two forces is also equal to 0 because the acceleration of the object is 0. It's moving with a constant velocity. However, these equations contain three unknowns, as we notice. It is T, N, and F sub k. Two equations are not enough to solve for these three unknowns. So what do? We look for a third equation connecting these parameters or these quantities. The third equation is naturally F sub k is equal to mu sub k times N. So we have three equations with three unknowns. We couple these equations and we solve for them. We eliminate the normal force in the beginning, and we obtain the value for the tension, which is given by mu sub k times small m times g all over cosine phi plus mu k times sine phi. That's the tension force. And the normal force is obtained by plugging in the value of the tension in one of the equations that contain the tension and the normal force. And the normal force is given by mg cosine phi over cosine phi plus mu k sine phi. And by this, we have demonstrated how we can apply Newton's forces, Newton's laws to study the motion of an object if we know the forces acting on it. And thank you very much for your attention.